In the last segment, we explained what is a public key encryption system, and we defined what it means for a public key encryption system to be secure. If you remember, we required security against active attacks, and in particular, we defined chosen ciphertext security as our goal. This week, we're going to construct two families of public key encryption systems that are chosen ciphertext secure, and in this segment, we're going to start by constructing public key encryptions from a concept called a trapdoor permutation. So let's start by defining a general concept called a trapdoor function. So what is a trapdoor function? Well, a trapdoor function basically is a function that goes from some set x to some set y, and it's really defined by a triple of algorithms. There's a generation algorithm, the function f, and the inverse of the function f. So the generation algorithm, basically what it does when you run it, it will generate a key pair, a public key and a secret key. The public key is going to define a specific function from the set x to the set y. And then the secret key is going to define the inverse function now from the set y to the set x. So the idea is that you can evaluate the function at any point using the public key pk, and then you can invert that function using the secret key sk. So what do I mean by inversion? More precisely, if we look at any public key and secret key pair generated by the key generation algorithm G, then it so happens that if I evaluate the function at the point x, and then I evaluate the inverse at the resulting point, I should get the original point x back. So the picture you should have in your mind is there's this big set x and this big set y, and then this function will map any point in x to a point in y, and this can be done using the public key. So again, any point in x can be mapped to a point in y. And then if someone has the secret key, then basically they can go in the reverse direction by applying this secret key sk. So now that we understand what a trapdoor function is, let's define what it means for a trapdoor function to be secure. And so we'll say that this triple GF F inverse is secure if in fact this function fpk is what's called a one-way function. Now let me explain what is a one-way function. The idea is that basically the function can be evaluated at any point, but inverting it is difficult without the secret key sk. So let's define that more precisely. As usual, we define that using a game. So here we have our game between the challenger and the adversary, and the game proceeds as follows. Basically, the challenger will generate a public key and a secret key, and then it will generate a random x. It will send the public key over to the adversary, and then it will evaluate the function at the point x and send the resulting y also to the adversary. So all the adversary gets to see is just a public key, which defines what the function is, and then he gets to see the image of this function on a random point x. And his goal is basically to invert the function at this point y. Okay, so he outputs some x prime, and we say that the trapdoor function is secure if the probability that the adversary inverts the given point y is negligible. In other words, given y, the probability that the adversary is able to output a pre-image of y is in fact a negligible probability. And if that's true for all efficient algorithms, then we say that the trapdoor function is secure. So again, abstractly, it's a really interesting concept in that you can evaluate the function in the forward direction very easily, but then no one can evaluate the function in the reverse direction unless they have this trapdoor, this secret key sk, which then all of a sudden lets them invert the function very, very easily. So using the concept of a trapdoor function, it's not too difficult to build a public key encryption system, and let me show you how to do it. So here we have our trapdoor function, g, f, and f inverse. The other tool we're going to need is a symmetric encryption scheme, and I'm going to assume that this encryption scheme is actually secure against active attacks. So in particular, I needed to provide authenticated encryption. Notice that the symmetric encryption system takes keys in k, and the trapdoor function takes inputs in x. Those are two different sets. And so we're also going to need a hash function that goes from x to k. In other words, it maps elements in the set x into keys for the symmetric encryption system. And now once we have these three components, we can actually construct the public key encryption system as follows. So the key generation for the public key encryption system is basically exactly the same as the key generation for the trapdoor function. So we run G for the trapdoor function, we get a public key and a secret key, and those are going to be the public key and secret keys for the public key encryption system. Now how do we encrypt and decrypt? Let's start with encryption. So the encryption algorithm takes a public key and a message as input. So what it will do is it will generate a random x from the set capital X. It will then apply the trapdoor function to this random x to obtain y. So y is the image of x under the trapdoor function. Then it will go ahead and generate a symmetric key by hashing x. So this is a symmetric key for the symmetric key system. And then finally, it encrypts the plaintext message M using this key that is just generated. And then it outputs the value Y that it just computed, which is the image of X, along with the encryption under the symmetric system of the message M. So that's how encryption works. And I want to emphasize again that the trapdoor function is only applied to this random value X, whereas the message itself is encrypted using a symmetric key system using a key that was derived from the value X that we chose at random. So now that we understand encryption, let's see how to decrypt. Well, the decryption algorithm takes a secret key as input and the ciphertext. The ciphertext itself contains two components, the value Y and the value C. So the first step we're going to do is we're going to apply the inverse transformation, the inverse trapdoor function to the value Y, and that'll give us back the original X that was chosen during encryption. So now let me ask you, how do we derive the symmetric decryption key, K, from this X that we just obtained? Well, so that's an easy question. We basically hash X again. That gives us K just as during encryption. And now that we have the symmetric encryption key, we can apply the symmetric decryption algorithm to decrypt the ciphertext C. We get the original message M, and that's what we output. So that's how the public key encryption system works, where this trapdoor function is only used for encrypting some sort of a random value X, and the actual message is encrypted using the symmetric system. So in pictures here we have the message M, obviously the plaintext could be quite large. So here we have the body of the ciphertext, which can be quite long, is actually encrypted using the symmetric system. And again, I emphasize that the key for the symmetric system is simply the hash of X. And then the header of the ciphertext is simply this application of the trapdoor function to this random X that we picked. And so during decryption, what happens is we first decrypt the header to get X, and then we decrypt the body using the symmetric system to actually get the original plaintext M. So as usual, when I show you a system like this, obviously you want to verify that decryption, in fact, is the inverse of encryption. But more importantly, you want to ask, why is this system secure? And in fact, there's a nice security theorem here that says that if the trapdoor function that we started with is secure, in other words, it's a one-way function if the adversary doesn't have the secret key, the symmetric encryption system provides authenticated encryption, and the hash function is a random oracle, which simply means that it's a random function from the set X to the set of keys K. So a random oracle is some sort of an idealization of what a hash function is supposed to be. In practice, of course, when you come to implement a system like this, you would just use SHA-256 or any of the other hash functions that we discussed in class. So under those three conditions, in fact, the system that we just described is chosen ciphertext secure, so it is CCA secure. The little RO here just denotes the fact that security is set in what's called a random oracle model, but that's a detail that's actually not so important for our discussion here. What I want you to remember is if the trapdoor function is in fact a secure trapdoor function, the symmetric encryption system is secure against tampering, so it provides authenticated encryption. And H is in some sense a good hash function. It's a random function, which in practice you would just use SHA-256. Then in fact the system that we just showed is CCA secure. It's chosen ciphertext secure. I should tell you that there's actually an ISO standard that defines this mode of encryption, of public key encryption. ISO stands for International Standards Organization. So in fact this particular system has actually been standardized, and this is a fine thing to use. So I'll refer to this as the ISO encryption in the next few segments. To conclude this segment, I want to warn you about an incorrect way of using a trapdoor function to build a public key encryption system. And in fact, this method might be the first thing that comes to mind, and yet is completely insecure. So let me show you how not to encrypt using a trapdoor function. Well, the first thing that might come to mind is, well, let's apply the trapdoor function directly to the message M. So we encrypt simply by applying the function to the message M, and then we decrypt simply by applying F inverse to the ciphertext C to recover the original message M. Right, so functionally, this is in fact, decryption is the inverse of encryption, and yet this is completely insecure for many, many different reasons. The easiest way to see that this is insecure is that it's simply, this is deterministic encryption. You notice there's no randomness being used here when we encrypt the message M, and since it is deterministic, it cannot possibly be semantically secure. But in fact, as I said, when we instantiate this trapdoor function with particular implementations, for example, with the RSA trapdoor function, then there are many, many attacks that are possible on this particular construction, and so you should never, ever, ever use it, and I'm going to repeat this throughout this module, and in fact, in the next segment, I'll show you a number of attacks on this particular implementation. Okay, so what I would like you to remember is that you should be using an encryption system like the ISO standard, and you should never apply the trapdoor function directly to the message M. Although in the next segment we'll see other ways to encrypt using a trapdoor function that are also correct, but this particular method is clearly incorrect. Okay, so now that we understand how to build public key encryption given a trapdoor function, the next question is how to construct trapdoor functions, and we're going to do that in the next segment.